Thanks very much, Francis. Good afternoon, everybody. I will be talking with you about water. And I've raised this question about the cleanest water on Earth. And I've raised these questions, how and also why, to sample and test pure spring water from the Elmvale Groundwater Observatory. Can everybody hear me okay? Great. So what I want to do is just a few words at the beginning about Arctic snow and ice, generally believed to be the cleanest water on Earth. And then I'll tell you a bit about the artesian flows of Springwater Township, and then the Elmvale Groundwater Observatory. And I'll show you some applications to water sampling and testing, also applications to drinking water and bottled water, and then finally a couple of things about the Athabasca River watershed. And then a few words right at the very end, an update for those of you who are interested in where we are with our new lab that we're building here. Okay, so if you're familiar with my research, you know I'm interested in heavy metals in the environment. And the ones that I focus on are the ones shown in red. Okay, and these are the ones that they have no physiological function, so they cannot be beneficial under any circumstances. Those are the elements that I focus on with my research. And my favorite one is lead. Okay, lead is my favorite. For many reasons, but mostly because it's a very valuable tracer. And it has a number of isotopes that we can follow. Okay, so I will give you some examples today about lead to help us understand the water. But because we're in Alberta, vanadium is also relevant. So I'll show you some results about vanadium that I think are relevant to the province of Alberta. Okay, vanadium shown here in green. Green means it's either essential to plants or animals or both. All animals require vanadium. And the concentrations I'll be talking about: parts per million, micrograms per gram; parts per billion, nanograms per gram; and parts per trillion, picograms per gram. But I also have to introduce parts per quadrillion, okay, ppq, or femtograms per gram. So if we were to go out to the North Saskatchewan River, pick up a water sample, measure magnesium and calcium, we'd be in the part per million concentration range. They're relatively abundant. Copper and zinc will be down in the part per billion range. They're trace metals. Cadmium and lead would certainly be in the part per trillion concentration range. And elements like rhenium, fascinating element. We don't have time for it today. I'll have to come back another time. Thorium, then we're talking parts per quadrillion. Okay, cleanest water on Earth. The cleanest water on Earth is generally believed to be ancient Arctic ice. So here we are in the Great White North of Canada, okay, in the Arctic. And ancient Arctic ice is thought to be the cleanest water on Earth for two reasons. One, because it's atmospheric water that is condensed. But two, if it's ancient, it predates human activities. And that's why it's clean. So it's generally believed to be the cleanest water on Earth. Okay, ancient Arctic ice. Now, to measure heavy metals in ancient Arctic ice, you need a very clean laboratory. And that's what we set up at the University of Heidelberg in Germany, probably the cleanest clean lab in the world. It was a clean lab, but it was also metal-free, so that you can measure metals in ice cores without contaminating them. So filtered air, everything made of plastic, and a sector field ICP-MS, which is really sensitive, okay? But the issue with ice cores is not sensitivity. The issue with ice cores is contamination, avoiding contamination. It's the number one problem doing trace metal analyses in environmental samples like water. So just to summarize all of this work that we did, we looked at 15,000 years of ice, 300 meters of ice. Atmospheric lead pollution in Canada did not begin with the introduction of leaded gasoline. It did not begin with the Industrial Revolution in the 18th and 19th centuries. It did not begin with lead mining in Germany in the 10th century. It did not begin with the lead mining by the Romans 2,000 years ago when they mined 100,000 tons of lead per year. Okay, it began 3,500 years ago with lead mining in Spain and the lead trade in the Mediterranean basin. Okay, so atmospheric lead contamination in the Arctic of Canada began 3,500 years ago. Okay, so the Great White North hasn't been white for a long time. Okay, this applies also to silver, arsenic, bismuth, cadmium, copper, antimony, thallium, and zinc. These are chalcophile elements. They're enriched in metal sulfides. Okay, so when the Spanish were smelting lead ores, they were not only releasing lead, they were releasing these elements. Okay, and we see them in Arctic ice 3,500 years old. So we've measured these in ice going back 15,000 years. So ice cores are fantastic archives. The cleanest ice layers are between about 5,000 and 8,000 years old. Those are the cleanest ice layers for lead. The average lead is 5 parts per trillion. I want you to remember that number. 5 parts per trillion. Okay, a part per trillion is like taking a liter of water and throwing it into Lake Huron. Okay, it's a very small number. That's how clean the ice is, 5 parts per trillion of lead. Okay, so the purpose of my presentation today, I've asked a very simple question. I asked this question about 8 years ago. Okay, we've added a lot of lead to the environment through the atmosphere, and it's accumulated in our soils. Very simple question. Is that lead slowly leaching from the soils into our groundwater? Okay, that can't be a tough question. How hard can it be? Okay, I've been working on this for 8 years now. These are the elements that we've measured in the groundwater from the Elmvale Groundwater Observatory. All of the elements that you see here, we've measured. Okay, so the story that I'm telling you today is the story of lead, but if we had 6 to 8 more hours, I could tell you about all of these other elements. Each one tells a different story, all fascinating. So the spring waters of Springwater Township. Here we are, southern Ontario. 90 minutes north of Toronto is a village called Elmvale, okay, named after the elm tree, which has since been wiped out by the Dutch elm disease. In Springwater Township, okay, in Simcoe County, just 90 minutes north of Toronto, and Springwater Township gets its name from the abundant springs that are found in this area. Okay, so this name is very logical. There's a lot of artesian springs, and the water is simply flowing. And this is an example of one just down the road from the Elmvale Groundwater Observatory. This one is actually used for a fish farm. I think it's Arctic char that they raise here. Now, there's a number of artesian flows in this area that I've been sampling and testing, but I'm going to tell you about my favorite one. Okay? Site 41, you'll hear me talk about Site 41. The county of Simcoe had planned to build a landfill here. Okay? The county of Simcoe had planned to build a landfill here, just so you know roughly where it is on the map. And there's a little farm here called the Johnson Farm, the old Johnson Farm. Okay? And this farm has an artesian flow. This is the artesian flow at the Johnson Farm. But what I need to tell you is my parents bought this farm in 1972. It's still known locally as the old Johnson Farm, but we've owned this farm property for a bit over 40 years. Okay, so here I am in 1972, and I was so thrilled that my dad bought a farm because I just wanted to go there and hang out. And that farm completely changed my life. So this is what the farm looked like in 1938. It's an old low-angle aerial. Here's the artesian flow, and it's the water supply for the farmhouse. Okay, so this water just flows, and people live there and drink it. I've never lived here. Okay, I visited many times, but I've never actually lived here. This is the artesian flow. Here I am now, University of Bern in Switzerland, with my first laboratory for ion chromatography. And this water became my reference water in my lab. I'd bring it back to Switzerland, and I would use it to check my analytical equipment, specifically the retention times on my analytical columns, to see if they were performing well. So this is a very clean water, and I used it for measuring anions and cations when I was at the University of Bern in Switzerland. So I've been testing this water for a little bit more than 20 years. And it gets more interesting all the time. Okay, this artesian flow, the water has a pH of 8, which is what you'd expect for a groundwater in equilibrium with calcium carbonate. But it's a Devonian dolomitic limestone, so we have both calcium and magnesium, about 175 milligrams per liter of carbonate alkalinity. So this is the major element chemistry of the water, a typical carbonate groundwater, okay? And the depth of this artesian well, 13 meters. And I need to point out that we have never detected tritium in this water. Okay, so what does that mean? That means this water seems to be older than the bomb testing, but we don't know how much older. Okay? But on the neighboring farm, the Tumulder property, they have a shallow well also, an artesian well, with plenty of tritium. So we know that these shallow groundwaters generally are quite young. Okay? And by that I mean recent. By that I mean less than approximately 50 or 60 years. I'll come back to that. Okay, this is recent groundwater. So when I was done at the University of Bern in Switzerland, I moved to the University of Heidelberg in Germany, and I set up a clean lab for looking at trace metals. And that's what I want to talk about today, is the trace metals in this water. So the trace metals in groundwater. So here's this artesian flow again on the farmhouse property. Notice it has a brass valve. Okay? So you all know that brass is a copper-zinc alloy, but maybe you don't know that it contains lead. Lead is added to brass to make it easier to machine. Okay, this is a scanning electron micrograph. So brass contains between 1 and 5% lead. Okay? So we did a time series. This is lead in parts per trillion. This is our first water sample. When you first open the valve and collect a water sample, you have 5,000 parts per trillion, or 5 parts per billion of lead. Okay, that's half the drinking water guideline. But if you collect the water with time, you have less and less lead. Okay, as you flush out the water from the system. That's the first draw of water. And this, whether this is really fully flushed or not, is an open question. But you can see we're down to 20 parts per trillion. Okay? We see the same picture for all of these metals. The brass is a source of all of those metals. So obviously I can't use this water for research. But what we did about 5 years ago, we removed the brass valve. Okay, we opened up the flow. Here you can see the water coming out of the ground. Okay, and it was replaced with stainless steel. So now there's a stainless steel valve. That was done by Tommy Nurnberg. Thank you, Tommy. He's the only person I would have trusted to do this work. Okay, if we do a lead time series now, we notice all of the lead concentrations are below 10 parts per trillion. Okay, so we've eliminated the effect of the brass. So that's good. So when I go there and I drink this water, okay, I don't have to worry about the lead from the brass valve. But can I use this water for scientific testing? Okay, it's fine water for drinking, but at the end of the day, we still have water coming from old steel pipes, right? And these are galvanized steel pipes. So if I were to show you some data on metals and groundwaters from galvanized steel pipes, hopefully you'd look at the data really critically. Okay? So I thought, wouldn't it be nice to do a groundwater research well in titanium? Okay, but before we did this work in titanium, I asked Tommy to make some titanium water bottles. And we did a leach test. Okay, we took these water bottles, filled them with concentrated nitric, left them for a month in the clean lab, and guess what? The lead leaching from the titanium. Much more lead leaching from titanium than from stainless steel. Okay, I'm so glad we didn't put in a titanium well. We'd only be measuring our own lead contamination. Okay? So no titanium well. For us, the first well that we put in is surgical stainless steel. Claire Patterson, Caltech, 1969, Geochemica, published the first paper on lead in Greenland ice. He showed that stainless steel 316 surgical contains no significant lead and doesn't contaminate his ice samples. Okay, so this is nice for drinking, but it's not going to help us with the research. So what is this Elmvale Groundwater Observatory? So here is the farm today. We've planted 25,000 trees over the past 40 years. Here's the original well beside the farmhouse. And we've put in 2 new dedicated groundwater sampling wells. Okay, 2 new wells. The first one, surgical stainless steel. And the second one is high-density polyethylene. And again, they're artesian. They're shallow. They're 13 meters, and the water is flowing all the time. Why is that so important? I don't want to measure what's leaching out of the pipe. I want to measure what's in the water. I want to sample a flowing well. Okay? It's a fair bit of work putting in one of these wells, but it's a great way to learn about geology and hydrology. So this is a cross-section of these research wells. Again, 13 meters, and we have almost 13 meters of almost a pure clay. It's a glacial lake sediment. It's a fine-grained clay. And down here at the bottom, where we have our aquifer, this aquifer is a medium to coarse-grained sand. Okay, that's the water-bearing layer. It's under pressure, so you punch a hole and the water flows up to the top. That's roughly how it works. Okay, so the plastic well we put in hydrologically upstream from the steel well, so the water's flowing from the plastic well to the steel well. And a friend in the area built a little cabin to protect these wells. So this is the Elmvale Groundwater Observatory. Okay, a stainless steel well, and then the plastic. This is special plastic from Denmark. It's a metal-free plastic. We brought it to Germany. We cleaned it in acid, and then we packed it and shipped it to Canada, and then we installed it. Okay? And these valves that you see here were also built by Tommy. Everything was cleaned in acid and then installed. Okay, so here's the 2 wells. And if you go to YouTube, groundwater research wells, you can actually see the water flowing and listen to the sound. It's not as big a hit on YouTube as that Gangnam thing from Korea. Okay, we haven't had so many hits, but give it time. We might get there. And since they were installed, I haven't recalculated this. This is an old number, but the volume of water has been exchanged at least 40,000 times. Okay, so how clean are these wells? Well, here's the original artesian flow, 12 ppb iron. The stainless steel well, 8 ppb iron. The plastic well, 4 ppb iron. I don't even care about iron. I'm just showing you this because even if you're only interested in iron, the composition of the well has an effect on the results, even at the part per billion concentration. That's the point. Okay, if we look at our lead concentrations, this is parts per trillion. They're now much lower, okay? That's our limit of detection, 60 parts per quadrillion for lead. If you look at some of the values, they're around a part per trillion of lead, but there's a lot of noise. Why is there that noise? Okay? The only thing that I can come up with is the air that we breathe, the aerosols in the air that we breathe, the fine aerosols below 1 micron, the enrichment of lead in those aerosols. So our bottles are being contaminated by ambient air. That's my interpretation. So how clean is the air? Well, what we've done, James designed this and Tommy built this. We've built, that's the royal we, Tommy built, laminar flow clean air cabinets. Okay? So now we do our water sampling inside the clean air cabinet. So we have a clean bottle that's clean for 3 months in clean acid that we've distilled twice in nitric acid in a clean air cabinet. Okay, and then we open it up inside our well, right? Inside our clean air cabinet. We have a laser particle counter, and we can see the ambient air has more than 1 million particles per cubic foot, larger than 0.3 microns. More than 1 million particles. That's the air that we're breathing. Okay? But in the cabinet, 0 particles. 0 particles. I must say, Tommy's built the best clean air cabinets I've ever seen. So inside the cabinet, 0 particles. So how clean is our water? Okay, this is where we're trying to get to. The first question is, how clean are the bottles? Okay, so here's lead concentrations in Teflon bottles. Teflon bottles. These are special clean Teflon bottles, cleaned in clean acid in a clean lab, $50 each. The data is horrible. Okay, I don't like these bottles. For us, they didn't work well at all. Okay, I don't like Teflon bottles. Low-density polyethylene bottles, the data's kind of all over the place. This is in the clean air cabinet. I think that's from the bottles, even though the bottles were cleaned. I don't think you can actually clean these bottles. Okay, high-density polyethylene bottles. Yippee, we've got a bottle that we're happy with. Okay, all of the lead is around a ppt. I think now we're beginning to measure what's actually in the water. Okay, the high-density polyethylene seems to be doing well, and we're getting closer to the true concentration of lead in the water. This is a summary of a comparison with our wells in the ice. I won't bother with all the details. What I want to show you, chrome in our groundwater, significantly less than in ancient Arctic ice. Okay, by a factor of 3 times. The lead concentration, on average, 5 times less than ancient Arctic ice. So the lead in the groundwater from the plastic well sampled in the clean air cabinet is much less than in the cleanest ice layers from the Arctic. And I have to emphasize this point. When we talk about the cleanest water on Earth, maybe it's not ancient Arctic ice. Maybe it's the water right underneath our feet. So the Elmvale Groundwater Observatory, what I want to do here is develop this as a scientific reference standard of water quality for scientists worldwide. Okay? That's where I want to go with this. So you're probably going to ask the question, so what? We're here in Alberta, right? Things look different here in Alberta. Here's a recent paper, Oil Sands Development Contributes Elements Toxic at Low Concentrations to the Athabasca River and its tributaries. Okay, what did they use for plastic bottles to do their sampling? Okay, high-density polyethylene. Okay, so that's really great because we've just seen it's good for lead. Okay, so high-density polyethylenes, they could be perfect for lead. I mean, if they're properly cleaned and all the rest of it. But, and there's always a but, okay, they're horrible for vanadium. They're horrible for vanadium. Okay, so here's vanadium over here on the left. 2 different wells, low-density polyethylene bottles. We've got about 20 ppt vanadium in the groundwater. Okay, the high-density polyethylene bottles, what we're looking at here is not lead in the, or vanadium in the groundwater. This is vanadium coming from the high-density polyethylene bottle. Okay, it's important to understand when you're doing trace analysis what you're actually measuring. In this case, we're not measuring vanadium in the groundwater. We're measuring leaching of vanadium from the plastic bottle. This is getting closer to vanadium in the groundwater. Okay, so HDPE bottles suitable for many trace metals, including lead, but not for vanadium. Remember, that's the element that I said is relevant here in Alberta. Okay, so if you're interested in the environmental impact of the oil sands development, and you're going to collect some snow, or you're going to collect some water, you have to think about what bottle are you going to use. Okay, what are the most highly enriched trace metals in the Athabasca bituminous sands? It's not lead, it's not arsenic, it's not cadmium. It's vanadium and nickel. Okay, so the low-density polyethylene bottles, great for doing studies of vanadium. High-density polyethylene, really lousy. I know it doesn't sound really exciting before you plan your sophisticated scientific study, which kind of bottle are you going to use? But you know what? You have to start there. Do you have a question?
Yeah. Also, the amount of time that you use the bottles, lower concentration.
Very good question. Absolutely. Yeah, leaching time. And remember, you have to acidify the water sample to preserve the metals in the bottle, right? So when you acidify your water sample, you want to bring it down to below pH 2, and you're promoting leaching. So if there's metals in that plastic, the longer your sample sits in there, the more metal you're going to have.
But if you like reuse the bottles and like wash them.
Can you get the vanadium out of the plastic? Very good question. Nice research topic. If vanadium is used as a catalyst for HDPE, and I got that from a reliable source, it's all through the plastic. It's not coming out. Okay, applications. A couple of applications here. One is, as I said, I want to develop this as a reference material for studying trace metals in water. When we look at metals in the atmosphere, okay, looking at metals in soil solutions, their transformations, their release, measuring metals in the aquatic environment. This water is a very valuable reference material for studying all of these processes. One application that we've used already is bottled water. Some people actually drink bottled water. So we've documented the contamination of antimony leaching from PET plastic, lead and arsenic leaching from glass. This water from Elmvale was our reference water. This is how we found out about all of this leaching, okay, because the antimony in bottled water is so high, and in this groundwater it's so low. Fluoride is commonly elevated in bottled water, uranium sometimes above the drinking water guidelines. Lithium and beryllium vary by many, many orders of magnitude, right? So again, this is our reference water for documenting some of the problems with bottled water. And this is why last year when the chairman of Nestle came to visit University of Alberta, I actually donated to Nestle a reusable water bottle from the Elmvale Water Festival. Okay, the other application, how to sample water for trace metals. Okay, so I mentioned this landfill that the county wanted to build. I had a chance to do some sampling here. I wanted to know the background chemical composition of the water. Okay, our data for these trace metals are typically 1,000 times lower than data from the Ministry of the Environment. And I was trying to understand, how can these differences be so large? So I went out with these guys one day to watch them do their water sampling, okay? And this is some of their aluminum concentration data. They've done the sample collection. I've done the measurement. And notice that we have up to 300 parts per billion of aluminum, okay? So if you know something about soil chemistry, this raises a red flag. 300 parts per billion aluminum at a pH of 8? What is going on here, right? Our data is never more than 3 parts per billion for aluminum. Okay, so our data is always much lower than this. So what is this? Okay, well, at a pH of 8, groundwater in equilibrium with gibbsite, we know will not have more than 3 parts per billion of aluminum. You can't have that much aluminum in solution. It'll precipitate as aluminum hydroxide. Okay, so our value is consistent with the theoretical maximum for groundwater at pH 8. So what is going on here? When they do their sampling, they pump the water and they stir up the colloids and the particles in the aquifer. Okay, and then they remove the particles by filtration, but the colloids are left behind and the colloids go through the filters. So what happens is we're adding colloids, and that adds trace metals. Okay, but these are not dissolved. So removing the particles by filtration, the bad news here, the anionic and cationic trace metals are affected differently. Okay, so we get similar values for arsenic, but for things like lead, the values differ by 3 orders of magnitude. So their data is an artifact of how they've collected the sample. Okay, and the blank values for the filters. We have not yet found a filter that's clean enough to allow us to filter our water samples. We never filter a water sample because a cleanest filter cleaned in a clean lab, the blank value is unacceptable. Okay, I've used this water for public education and awareness. Okay, so I started an annual water festival in the village. This is the logo of the water festival, Celebrate Water, because this is fantastic water. And I created a foundation, the Elmvale Foundation, which is a federally registered charity for environmental education. And you can find more information on the website, elmvale.org. But don't go there today because it's badly out of date because I haven't had time to update it. Here's Site 41. This was going to be a landfill. I think we helped to raise some awareness about the quality of the water in the area. The First Nations got involved. They were welcomed to the area by the local farming community. And I think we can say that's maybe the first time in Canadian history where First Nations and farmers were working together hand in hand. And Site 41 was shut down completely in September of 2009, and the land has been reverted back to agriculture. Okay, so a quick news update. Okay, very quick news update. Ego 3. Okay, we haven't been sleeping. So we have these two groundwater wells at a depth of 13 meters. We've put in a new one. It goes down 60 meters. It's also a flowing artesian well. Okay, so we did this in May of 2012. It was actually quite an operation. It took us 10 days to do this hole. It's actually a lot of work. Not for us. We sat around drinking coffee, but for the guys that actually did the work, it was a lot of work for them. But what we did this time is we collected the cores. This is why it took so long. We collected the sediment cores. Okay, so we have 60 meters of cores. And Riley Mulligan, a master's student at McMaster University, has reconstructed the geology of the area for us. So we can see the lake sediments. We can see the glacial till. So we have the glacial history of the area. You can see the varving and the lake sediments, which is really cool. Okay. And I learned a lot about the geology of southern Ontario because these glacial tills, it's amazing. Every rock type from the province of Ontario is in that till. It's amazing how the ice was grinding up the entire province. But the beautiful part was once we got down to the bottom, we hit sand full of water, okay, full of water, and we had a flowing artesian well. Okay, this is the aquifer sand. A very scientific illustration here, okay? And we have a flowing well, which is really beautiful. This is a photograph I took of the particles in the water. So we let this thing flow for several days before putting on the valve, okay? And this is the valve that Tommy made. It's his first project here at the University of Alberta. And there's a valve in action, surgical stainless steel. It's not in contact with the water. And again, we have a flowing artesian well. And this is Jamie and Rick, the well drilling guys, drinking with an Elmvale Water Festival bottle from our new valve on our new well. And it's delicious, delicious water. And we have a new tiny little cabin, and now Tommy will build a clean air cabinet so that we can start to slowly do the water sampling here. And I'm really indebted to these guys because this is a $100,000 job. I only had $30,000. Okay, so they donated the rest. So they were really, really generous, and I'm really grateful to them for that. Okay, last application, the Athabasca River Watershed. Okay, so you're probably going to say, okay, what does this have to do with Alberta? Who cares about clean water in Ontario? We're here in Alberta. The Athabasca River has caught my attention. Fascinating, fascinating facts and misconceptions. The more I read about the Athabasca, the more frustrated I get, especially as regards trace metals. I found this cartoon. I love this. Here's a journalist. So how bad is the heavy metal contamination in these waters? Let's just say we've started fishing with magnets. Is it really that bad? So what are the facts? At the end of the day, scientists just want to put the facts on the table. So what are the facts? So let's look at the metal inputs to the Athabasca River from the tailings ponds. I'm going to do this really quickly. Our report 2012, Martin Savard, Geological Survey of Canada, state-of-the-art looking at leaching from the tailings ponds into the Athabasca River. Here's the cross-section. Here's the tailings ponds. They think the water's moving like this toward the Athabasca River, and here's their groundwater sampling wells. Well, it's fascinating. They've decided that total metal concentrations are generally very low. Okay. In fact, the concentrations are so low that it's not possible to do any modeling with any of the data. I mean, a lot of the values are less than the detection. Okay? They couldn't do lead isotopes in the groundwater. Okay? But let's look at some of the data for vanadium. This is in parts per billion. This is the groundwater flow from a high hydraulic potential to a low hydraulic potential. So the arrows here are showing flow in this direction toward the Athabasca River. Let's look at their data. 0.2 parts per billion, okay, closest to the tailings pond. 8 parts per billion. 12 parts per billion. The highest vanadium is furthest from the tailings pond, right beside the Athabasca River. If somebody can explain that to me, I'm all ears. Okay, it's just caught my eye. I don't pretend to understand it. I'm just saying that picture is not clear for me. And a bunch of other values, like less than the detection limit. And the detection limit, 0.1 ppb. Not a great detection limit for vanadium, right? So to me, this data is really, I'm not sure what it's telling us. Okay, but the maximum is furthest from the tailings ponds. Here's detection limits with sector field ICP-MES. This was our machine in Germany. Here's a part per trillion. This is a logarithmic scale. Here's a part per quadrillion. Notice our detection limit for vanadium, about 10 parts per quadrillion. Okay? Our new lab will be at least as good as that, probably 10 times better. I think we can reach 1 ppq vanadium. But if we look at their detection limits, they're 10,000 times higher. The detection limits are inadequate for understanding heavy metals leaching from the tailings ponds going into groundwater. That's my message. Okay? And if we look at their nickel data, parts per billion, the highest values are furthest away from the tailings ponds. And again, less than detection, a detection of 0.2 ppb, not really suitable. Okay, the highest values furthest from the tailings ponds. Finally, an update of the swamp lab. I will eventually start work. I promise. I've been here about a year now. This is what our swamp lab is looking like. Okay, it's just about done. This is the student clean lab for acid preparation, vessel cleaning, sample digestion. No equipment in it yet. And this will be the clean lab for the 2 ICP mass spec machines, and both of those machines have been ordered. So it's still a work in progress, but hopefully in the autumn we can begin to do some measurements of our own. Okay, to summarize, we've created a dedicated sampling facility for the study of trace metals and natural fresh waters. The concentrations of many elements are at or below the levels that we find in ancient Arctic ice. And the extreme clean lab methods that we use, and we've developed for the ice cores, actually we have to use them for our water samples too. Okay, that's the message. And the latest result, just received at an ungodly hour this morning from Ian Clark, University of Ottawa. I've given him water samples. He's measured 129 iodine, okay, in all 3 of our wells, okay, and we can conclude now that all of this is recent groundwater because he's measuring traces of 129 iodine. So think about that. This groundwater that's so clean, it's not more than 50 or 60 years old. So the dirtiest rainwater in the history of North America goes through the soil, and what comes out is what I've shown you here. Okay? Soil is an outstanding water filter, and none of my colleagues, okay, here in soil science, to them, this is hardly new. Okay, they know that. But what we're trying to do is put the numbers on. Thanks very much for your attention.